Okay, so it's going to be a second lecture on divide and conquer. Last time we did quick select, right? This median of medians thing. We almost figured it out as a class. That was pretty cool. And then we did closest pair of points, right? And there we did this like narrow band thing and this packing argument. So yeah, those felt a little more like divide and conquer in you're really dividing up the input and things like this. So this will be a little bit funnier. These are going to be kind of like numerical algorithms, and it's going to do divisions in other clever ways. Okay, so we'll see. So um, okay, so multiplying integers. So here we're going to really focus on like multiplying bit strings. I'm very careful about the representation. So you have some bit string 0, 1 and 0, 1, 0, 1, 0, 1, and you want to multiply and output the corresponding number. Yeah, and you're really counting like elementary operations, 1 times 1, that's one operation, things like this, right? Obviously, in any programming language, multiplying two integers is one line of code. That's not how we're thinking about it here. So, okay. So if you were to do like some multiplication like this, 1, 2, 3, 4 times 5, 6, 7, 8, like what do we learn in like grade school or elementary school? Does anyone call it grade school? I don't know. Yeah, so at least I was taught you start at the 8. Yeah, and so then you get like, yeah, 32, you carry a 3, and you get like 27, you carry a 2, and you get 18. There's something like 9. Hopefully I did that correctly. And the next line is like, okay, 7 times 4 is 28, and then 7 times 3, I guess 21, so then you get 23. It's actually kind of hard to do this in your head. 7 times 2 is 14, you get 16. 7 times 1, so you get 8 or something like this. And you just go one by one, and if you can multiply two single digit numbers, you should be able to ultimately multiply arbitrary digits. You kind of build out this table, and at the end you add everything up. Okay, so uh, like how long does this take in terms of digits? Say there's two n-digit numbers. I didn't do the last two steps because I was kind of afraid to make a mistake, but how long would it take as a function of the number of digits? Yeah. N squared. So one way to see that is that each number here gets compared to or multiplied against every number here. And that would be true for all of these. So ultimately every pair of numbers or every pair of digits from x and y gets multiplied and compared with each other. So this is an n squared time algorithm and the one you're taught in class, right? And the question, didn't mean to erase the B. The question is not error. The question is, can you do better? Yeah, can you do better than n squared? And historically, this was an important question. So I think in like 1950s, there was a very famous Russian mathematician named Kolmogorov, who has done a number of things, including sometimes he gets credit for setting up the axioms of probability theory. But he has, anyways, one of these kind of legendary mathematicians, and they're just kind of getting into computing, or even before computers, they're just thinking about computation more logically, the idea of following steps and stuff, knowing that computers are kind of coming on the horizon. So, so he asked, to his whatever graduate math seminar or something, can you do better than n squared? And he conjectured you couldn't do better than n squared for multiplying integers, right? Because doesn't it seem obvious that like you've been multiplying integers our whole life, right? And I don't think we ever second guessed uh, this standard algorithm. At least I certainly didn't. Um, yeah. And then I think he was a grad student at the time, uh, but I think early 60s. I used to have a slide with the dates and somehow I deleted it. Um, he actually said, oh, you can do better than n squared. And I think that was very surprising, right? That was very, first you feel dumb because like, oh, I didn't even know how to multiply integers. Like, but some level like, oh, if you don't even know the best way to multiply integers, maybe all sorts of seemingly obvious things, one can in fact do much better. I mean, I think this had a profound impression on mathematicians who thought they knew everything there is to know about multiplying two numbers, but apparently there's something different about computation, a slightly different perspective. So while of course, in practice, you'll never be too concerned about multiplying two integers. This has some historical significance. Okay, so any ideas for doing better? I hope I didn't give it away too much. Did I give it away? It's going to be like divide and conquer. So what can you possibly divide? There's only two numbers. Okay, so by fast exponentiation, I just want to make sure, like, for example, this is sometimes used when getting certain eigenvalues or something. So it could be a matrix, it could be a number, but something A, right? And you want to get A to the n for some very large value of n. Okay, so of course a number you just multiply with itself. Maybe that doesn't seem so interesting, but with a matrix, each time I multiply A with itself, that's a big, n by n by n computation and stuff like this, right? So you would like to avoid doing this n times. Okay, so what would be a faster way to do this for those who don't know the answer but still have the courage to guess? I'm not sure if anyone's in that part of the Venn diagram. So the naive way, if it was trying to raise a matrix A or a number A to the nth power, is to just multiply with itself, with itself, with itself n times. Whatever that operation is, I'll do it n times. And I'm claiming you can try to get something closer to like log n or something. Any ideas? Yeah, something like this. an by 2 times an by 2. So if you can figure out an by 2 or an over 2, then you just have to do one more multiplication. Yeah, and so yeah, that would be like a top-down approach. Often you see it more presented as, oh, first I multiply a, then I get a squared, then I get a fourth. All these kind of divide and conquer things, you can kind of look at it bottom up if you really want to write some C code that like doesn't waste any time on things. But yeah, you can just build bottom up. And then you're going to get something like log n to raise to the nth power. Yeah. So the answer is that's not what we'll do, but still I'm happy that we had a chance to discuss this because that's not a bad example of divide and conquer. Yeah. Oh, similar to the way we multiply. Well, we haven't discussed how to multiply matrices fast. Uh, I think maybe there's some similarities, but I'm not quite sure how to discuss it since we haven't discussed matrices. Yeah, any ideas? Oh, um, this isn't binary? Oh, so how do I interpret a 10? Is that the 0, 1? Um, okay, so maybe I can try to loosely describe this as like particular patterns in the digits that you can try to leverage. Something like can you basically do something clever by looking at the digits correctly, and there's some special cases you can do better. So maybe there's things like this certainly in practice. Like sometimes bit shifting is faster than other things and stuff like this. But I don't think those practice wins are going to count in our computational model here, and certainly what I have coming up won't look like this. Yeah. Okay, so we're doing divide and conquer, and it's divide and conquer on what? The, the bit string. So that's what we're going to try. So we're going to try taking your bits and divide it in half. Okay, and then work from there. So, okay, so here's X, and then I can split into two bit strings like this. One represents like the biggest, most significant n over 2 bits, and the least significant n over 2 bits. So I'll call it x1 and x2. Right. X1 and x2, right? And we'll do the same thing for y1 and y2. Okay. And so then you could write something like this. Okay, x is x1 shifted over n over 2 times plus x2. Y1 is, or y is y1 shifted over plus y2. I mean, that's nothing profound, right? I'm just making sure we're on the same page. So that means you can take something like x times y, and you can start factoring just plugging this thing in, right? So that's like x1, y1 times 2 to the n, and then you have these cross terms, 2 to the n over 2 plus x2, y2, right? Okay, so at some level, I can take multiplying n bits, two numbers of n bits, and turn it into 4 instances of multiplying n over 2 bits. Okay. Now, what would that running time look like? Okay, so first let's just model it. So, did I write it? Oh, yeah, if it multiplies 4. Okay, so where should we work? Okay, so if I wrote first t of n, what would this be? Yeah, just the modeling. 4 times tn over 2, plus maybe some linear work to put everything together at the end. Yeah, yeah. Two number, yeah. Maybe I could have wrote n comma n and n over 2 comma n over 2, and then you see the two factors. Okay. And if we write this as we start trying to do some quick recurrence tree stuff, right? This is a problem of size n. These are problems of size n over 2. Okay. And each one you're doing, work proportional to the input size. So you do n total work on the first level. How much total work do you do on the second level? 2n. There will be 4 terms of n over 2. And then, if I was going down here, what would this work level be? You can almost just guess. But it would be, right, it would be 16 terms, each of which contributes n over 4, and you'll get 4n. Okay? And then how tall will this tree be? Yeah, in particular log base 2 of n, sometimes it's helpful to be precise because this constant will matter. Okay? So our total running time is going to look like, oh, I'm summing from 0 up to log 2 of n. I'll put the n on the outside, 2 to the I. Yeah? And so what's this? Yeah, so this term in particular, so all you have to do when it's a geometrically increasing sequence is say, what's the dominant term? The largest term is going to be within a constant factor of the sum. So you're going to get n times 2 to the log 2 of n, just to do it slowly. And that's n squared. Okay? Throw some big O's around it. And then you're not cheating anymore. Okay? Okay, so that'll get you n squared. So we haven't actually won yet, but at least we're starting to break down the problem. Yeah? So this is indeed the right direction, but somehow we want to be more clever. So let's see. What's down here? Okay, good. An idea slide. So any ideas, right? So if yeah. Yeah. Okay. So when you multiply two n-bit numbers together, your output's going to be two n bits long, and that's okay. Yeah, we don't mind. Oh, okay. Um, okay, how do okay, if we go down, will there be some redundant multiplications? So, okay, so I will try writing, so that term here is going to look like, I'm not sure if I'll do a good job. I'll write x1, 1, y1, 1, 2 to the n over 2, plus x1, 2, y1, 1, plus, sorry, I'm being very clumsy, x1, 1, y1, 2, 2 to the n over 4, plus um, x1, 2, y1, 2. So that's just expanding out one of the terms. Uh, but in general, you're looking at various combinations of x1, 1, x1, 2, y1, 1, and y1, 2. I guess if you were splitting y1 into two halves, y1, 1 and y1, 2, it's a little bit notation heavy. And if you looked at something like this would be a combination of x1, multiplying these various things together, y2, 1, y2, 2. I mean, those would be the terms involved if I wrote out the full thing. And so I guess the point I'm trying to make is that the suggestion was that if we went one layer deeper and I enrolled one more, would there be some redundant calculations? But I think at this level, you can start to see, okay, so this term that's multiplying these various cross products together is going to be all different terms than like this one, which is multiplying different ones together. And I think that will also be true of the last two. So I think in general, because you're splitting up and you're not remixing them, it's not obvious, at least to me, that you're doing some clearly redundant thing at the next level. It seems like different terms are involved. Yeah. Okay. Okay. So this is very much approaching the trick. So here's my next hint then. Um, So look at this. So this is x1 plus x2. Remember, I'm not shifting x1 anymore, so this is not just equal to x times y1 plus y2. Okay, and then I just wrote out the kind of natural thing. Okay, so you stare at this, right? And do you see the trick? Or do you, what? Okay, so this middle term is what we're looking for, right? We're trying to get that term. And you could already compute x1, y1, and x2, y2 anyway. Okay. So if you're already multiplying x1, y1, x2, y2, then you can get this middle term by subtracting out this funny product. Okay, those middle two terms. Right? So now you're able to, with this trick, you're able to get or well, in this special case, you'll get two multiplications for a price of one. Overall, you're getting four multiplications for the price of three. Hmm? Right. Okay, I agree. Yeah. I feel like no one pointed this out last year. I don't know what Ryan was doing. Anyway, uh, but yeah, absolutely. Yeah, I was missing a sign. Okay. So that's, you know, simple in hindsight, right? But Kolmogorov missed it. Everyone missed it. Yeah. Okay. So good. Okay. So let's just turn this into an algorithm. This is the boring teaching part. I'll just first ask if we're going to do a recursive algorithm, we need a recursive spec. So anyone just, suggest a spec, give it a name, give it some inputs, and give it a sentence. Yeah. Yeah, I mean, I might be a little more careful to say like takes two n digit or yeah, numbers. I think it's good to specify like the type of your input. But yeah, nothing special, nothing tricky. And um, and I guess here would be as usual, the implementation looks way messier than it should be. Yeah, I guess we can go it a little bit slow. If there's no bits, the answer is zero. Zero times zero is zero. If there's one bit, multiply them together. Um, I guess, there's always this issue of like what happens when you divide by two, if it's an odd number. I guess here I took some kind of lazy thing where I said, okay, if it's an odd number, I'm just going to prepend a zero to the beginning and make it even. Okay. Uh, and then this awkward line, this looks way more complicated than it should be. It's just splitting the strings in half. And then here I'm adding the two strings together, x1 plus x2 and y1 plus y2. And then here's the three recursive calls. And then you just do the math at the end. Okay, this is not very deep, okay, but just writing it out for the sake of concreteness. Okay, so good. Let's just figure out the running time. Let's first model it. What does the equation look like? Yeah, plus. Yeah. Okay, so before we had 4 times tn over 2. That goes to n squared. Now we're down to 3. So hopefully this will be better. And okay, so you have some tree like this. Input of size n, inputs of size n over 2, inputs of size n over 4. Okay, and the work at each level is just summing up the problem size. In this case, it's linear work. So how much work in the first level? Okay, I will wait. Okay, what about the second level? Okay, 3n over 2. And in the third level? Yeah, something like 3 over 2 squared, so forth. In general, it's going to be, 3 over 2 to the I for whatever level I. Okay. And then how many levels are there? Yeah. Okay. So now, yeah, our total work looks something like this. Okay. And how do I solve this? All right. Look at the largest term. So you're going to get 3 halves to log base 2 of n. Right. So now we got this awkward thing with the logarithm in the top right corner again. I mean, n in the top right corner in particular. I want to get something in terms of like n down at the bottom so I can make some sense of this. And what's the trick? Yeah, how? Huh? Okay, well, I'll just do it slowly. This is the easiest way for me to remember how to do this. I write 3 halves as log base 2. I mean, 2 raised to the log base 2 of 3 halves. Log base 2 of n. Okay. And now I can interchange these, right? And 2 to the log base 2 of n is n. Okay. So now you're going to get n times n to the log base 2 of 3 halves. And then this is like n to the 1.58 or something. Did I write it down? Okay. Oh, yeah, yeah. Yeah, yeah, that's better actually. Yeah, so this, yeah, good. That's better. Minus log base 2 of 2, and that's just 1. So that'll get rid of one of the n's. So probably this is like the cleanest one. And to the log base 2 of 3. Don't know what that is. I put that into a calculator. I think it's 1.58. Yeah. Okay, so you do, substantially better than n squared with this trick. Now, to the best of my understanding, I looked this up a couple years ago, and I'm a little fuzzy on details. But not that long ago, like in the last 10 years, they got it down to like n. I think it's log n, but it might be there might be some constant here, 2 or 3 or something. Okay, so you can do something like n log n, but it's randomized. So that means our best that we don't have a deterministic n log n algorithm. We only have a randomized algorithm. And it's, as best I understand, going to use, among other things, techniques from the next section, which is on Fourier transforms, fast Fourier transforms. So somehow this problem is still sort of alive and well. I guess n log n is pretty satisfactory if that was indeed the bound, um, but it's still randomized. So like, somehow it needs to use some coin flips in order to get this fast running time. But you just multiply numbers, right? So this is absurd. Surely there's some way to get a deterministic algorithm. We don't know, right? Yeah. Lower bound? Oh, well, yeah, obviously n squared. Well, I think he would just kind of, you can't do better than n squared. I don't think it was too, well, you can't, I mean, if you had a proof of a lower bound and a proof of a better upper bound, like, I don't know, the world implodes in a black hole or something, right? Like, we'd be in a lot of trouble. So, no, I think he just said, oh, you can't do better than n squared. I don't think you can do better than n squared. And because he's so revered, it's just like, oh, okay. You know? Um, yeah, yeah. So somehow, yeah, I don't know actually if there's I should probably know, but I'm an irresponsible teacher. There may or may not be a lower bound saying that you need n log n. I mean, n is the obvious lower bound, but yeah, yeah, I don't know. I don't know, but it might be Googleable. I mean, this paper was the best upper bound. If there was a lower bound, we'd probably mention it. Yeah. Okay. But any questions? All righty. Okay. Then let's do this. Fast Fourier transforms, which is going to be a little bit heavier on the background, uh, but it's okay. So this is something that, as I understand, is quite useful actually in practice because engineers need to take fast Fourier transforms all the time. But actually, there's some very creative applications in computer science as well. One of them will be your homework, just like all these clever things where you can kind of use fast Fourier transform in clever ways. Um, there's like a whole kind of zoo. But to explain fast Fourier transform, at least from mildly first principles, I need to first go over complex numbers. Okay, just some basic properties. I won't prove anything from scratch, but enough to make sense of the algorithm. Relatively brief primer. Okay, so I think you all have seen at least this much before. So the idea is you kind of work in a two-coordinate system, a real part and an imaginary part, right? You introduce this imaginary number I defined by I squared equal to -1. Oh, what if -1 had a square root? Okay, I'll call that I. And then I can, sort of treat this as some kind of algebraic system where I have two coordinates, A plus BI. So B is sort of the imaginary part, something times the imaginary, and then the real part A. Okay. And it obeys simple rules that presumably you've seen before. You can add them in the obvious way. You can also multiply them. Okay, so if I take two complex numbers and multiply together, this should look very familiar to you. The only difference is that the C and the D, Ci times Di, gets you CDI squared. The I squared becomes -1. So that's where that negative sign comes from. Yeah, but otherwise it's just algebra as usual. We just add one more rule to the system. Okay. Once you start being able to multiply things, then you can start having polynomials, right? I can define a polynomial with a bunch of coefficients that can be complex coefficients with a real and complex part, okay? And say, oh, this polynomial is a0 plus a1x plus a2x. And I can imagine taking a complex number, plugging it into x, and just following the rules of multiplication. Yeah, so once multiplication is established, you have polynomials. And then you start getting functions that are limits of polynomials. Okay, so if I just ask you a priori, what's the exponential function of a complex number, that's a little confusing, right? It's like, But since the exponential function can be expressed as an infinite polynomial, okay, so e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. You may have seen this before, so on and so forth. Otherwise, it kind of shows halfway through, analysis class in the math department. Okay, so I won't prove it because it takes a little while to set up. Okay, but you can write e to the x as a polynomial, and each successive term gets you closer and closer to the true value. So in fact, if you truncate it at some point in the middle, you'll get pretty close to the true value of e to the x. That actually happens a lot in practice for various situations. Okay, so good. So now you have an exponential function of complex. And then you get this fantastic Euler's formula. Okay, so if you take some theta between 0 and pi as an angle, okay, and say, oh, what's e to the theta I? Okay, and then the actual real part and complex part is going to work out like this. Okay, so e to the theta I is actually going to get, the real part's going to be cosine theta, the imaginary part's going to be sine theta. And what this function is actually doing, as a function of theta, is it's actually spinning round and round and round. Okay? So that's just a fact, if you worked it out slowly. And so then you start getting things like Euler's identity. Okay, so e to the pi I, that's pi out of 2 pi, so that's 1/2 rotation around the circle. You start at 1, you go to -1. Yeah, and you do another one, you get back to 1. If you just do a quarter turn, you'll get I. You do 3/4 turn, you'll get -I. Okay, good. So those are just some ways to look and think about complex numbers. Okay, so the reason I had to do all this is because we're going to make critical use of something called roots of unity, which are only interesting in complex numbers. Okay, so fix some value n, could be 2, could be 3, could be very large. Okay, and an nth root of unity is any number a where a to the n is equal to 1. Right? So of course 1 is always a root of unity. 1 to the 100 is 1, 1 to the 1 is 1, 1 to the whatever is 1. Okay? But what are some other roots of unity? What are some simple roots of unity? Oh, okay, what's the next simplest one? -1. Okay, good. So -1 for any even n, right? Because once you square it, then you get 1. Okay, what would be like the next easiest? I. Okay, good. Okay, so I for n equals 4. Yeah, I squared gets you -1. Square it again, you get 1. Okay, but in general, how would you describe? Yeah, any number what? Oh, any number for n equals 0. Yeah, I guess that's true. Yeah, I'm not sure if that ever comes up. Yeah. Yeah, so let's say, I guess here I drew one for 16. Okay. And, uh, right. And so what I'm going to do is I'm going to take that unit circle and divide it up into 16 parts. Oh, I think so. Yeah, that would create some confusion. Okay. Um, but, look at this, right? So, and e to the 2 pi I over n, right? If I raise this to the nth power, the n disappears. You get e to the 2 pi I, that's 1. And if it was 2 pi I times 15 over n or something, and I raise it to the n disappears, and you get e to the 2 pi I times 15 or something, and then you get 1 to the 15, you get 1. Okay? And in e to the 2 pi I can be interpreted as just points on the circle. Yeah, so those are the nth roots. So it's all coming from this. Yeah, I mean, there's some very nice. There's a really nice book called Visual Complex Analysis that puts a lot of emphasis on this circle. Yeah, but okay. So I mean, this isn't the whole class of complex analysis, but yeah. Okay, does that much make sense? So these roots of unity has to do with rotations on a circle. Okay. Good. Okay, so now I can define what the Fourier transform is. Okay, so it takes as input a polynomial, which is maybe defined by its coefficients. So you really might get a vector of numbers, a0, a1, a2, a3, a4, which you interpret as a polynomial a0 plus a1 times x plus a2 times x squared plus a3 times x cubed. So in some sense, the input's a polynomial. In some sense, it's a list of numbers. Okay, and your output is going to, for the nth Fourier transform, it's going to evaluate that polynomial or interpret that list of numbers as a polynomial and evaluate it at all the nth roots of unity. So you evaluate at 1, evaluate it, 1 tick on the circle, 2 ticks on the circle, 3 ticks on the circle, and you're going to get all those values. Yeah. Why is this? Why would anyone want to do this? Or, well, okay. If you know the value of a polynomial at n different values, you know the polynomial, if it's a degree n polynomial. Okay. So if you get actually these n values, um, then you actually have a different representation of the polynomials. This is a kind of fundamental theorem of algebra type of stuff. Okay. And so, okay, let me make this more explicit. So there's also a conjugate version, okay, which is basically the same thing. Okay. Except you just list your output backwards. It's a little weird. I'll explain why you even make this distinction in a moment. Okay. But in the discrete Fourier transform, it takes a list of numbers, it outputs a list of numbers, evaluate at 1, first we're unity, unity squared, unity cubed, unity fourth. And the only difference here is you're going to go backwards on the circle. You evaluate at 1, then go backwards. From your point of view, I'm so confused. 1, backwards, backwards, backwards through the circle. Okay. Yeah. All right. Okay. Monkey see, monkey do. So, um, okay. So that's obviously if you can implement one of these, then you get the other one for free. You just run it and you list the terms backwards. So it's not, from a computer scientist point, not super interesting. The reason it's important is that they're basically inverses to each other. Okay. So I take your polynomial as a list of coefficients and I evaluate at the nth roots of unity going forwards. Okay. And that gives me n new values. And I think of that as a polynomial. Okay. And I evaluate it at the nth roots of unities going backwards. I mean, I do the conjugate Fourier transform. And you get n new numbers, right? Those n numbers are going to be the original coefficients you started with, scaled up by a factor of n. So this, if you just kind of work through it and you multiply things out, you're secretly doing some stuff with an orthogonal basis in case you are coming from linear algebra land, and that's sort of what's going on. It's a unitary transformation appropriately seen. It's not so important for us. What's important is that with a Fourier transform, you also essentially have its inverse, okay, in terms of fn star, which is just evaluating it backwards. Sorry? Oh, okay. Yeah. So, okay. I know everything's still a little abstract. So, okay. Well, let me at least first state this here. Maybe you guys can all guess. So if I want to evaluate the nth Fourier transform on a polynomial's n coefficients, how long do you think we can, how fast do you think we can do it? So n squared, first of all, is obvious, right? Because that's plugging everything. And n was the first guess, and surely you need at least n. So anyone else think we can do it in n? Okay, so we're going to try to show is actually n log n. And I don't know if you can prove we can't do n, but we don't know it in n. N log n is the best we know, at least best I know. which is usually the best we know. Okay. All right. So Fourier transform is a little bit obviously like why do I care about coefficients and who cares that fn is equal to fn star? That's nice, but I'm in algorithms class. So here's maybe an application that's like a little bit more compelling. Okay. Suppose I gave you two polynomials. Okay. And I want to multiply them together. So I want to get the polynomial multiplying them together. That would be r here, right? And just to make like the exponents match, the coefficient, the 10th coefficient for r is going to be like a0 times b10 plus a1 times b9 plus a2 times b8 and so forth. It's just kind of like zip them together because that's how you're going to get the 10th power, right? x0 times x to the 10, x1 times x to the 9. Okay, so this is called a convolution sometimes. Okay, so this, of course, you can multiply in n squared time by just doing it one at a time, right? But the suggestion is that there's a very clever way to use fast Fourier transforms to multiply these two polynomials of degree n in n log n time, which hopefully is a more grounded, compelling application than this complex number mumbo jumbo. Any ideas? So the natural way to do is to make two loops, right? One looping through the first polynomial, the other looping through the second, and then just kind of filling out some table. I'm going to add this to this coefficient, add this to that coefficient. That would take n squared time. And I'm saying we can do something way faster, n log n, which is pretty impressive, I think. Suppose, okay, the first step is going to be for each of those polynomials, take the Fourier transform. What else could you do if you're supposed to use the Fourier transform? Okay, so you have these values of p. You've evaluated p along the circle, and you've evaluated q along the circle. That's the first step. It's that much. But what could you do next? You're trying to get r. Remember, if you know the values that a polynomial takes at n different points, you can get the polynomial back. Yeah, perfect. So because we have the opposite conjugate transform, right? If I knew the values of r at each of the points of unity, then I can apply the conjugate and get back r, right? So the question is, okay, how do I get the values for r at the endpoints of unity? Well, if you have the values for p and the values for q, oh, okay, the first root of unity, I just multiply those two values together. That's the value of r, right? So q of 1 is equal to p of 1 times, sorry, r of 1 is equal to p of 1 times q of 1. R of omega is equal to p of omega times q of omega. R of omega squared is equal to p of omega squared times q of omega squared. And you can get all the p of omegas and q of omegas very fast. You get those values fast, you zip them together to get the n values for r, and then you can turn that back into a polynomial. So something like this. So you first in n log n time, but this is better, you're going to evaluate the things. Okay. The only reason I'm doing 2n instead of n is because eventually r is going to be a 2n degree polynomial. So you actually need to do a little bit more. But then you get these values for r, and then you just flip it back. Okay. And then you get what you're looking for. Okay, so it's a little bit magical. right? Somewhere under the hood, we're using a very nice mathematical identity, fn star, is practically the identity, off by a factor of n. Yeah. Okay, so why can't you do this to multiply the n-bit numbers? This is a great question, right? Doesn't this look a lot like multiplying integers? Each digit is like a coefficient. So why don't I just apply Fourier transform? Well, you could just think of each the first digit as A0, the second digit as A1, the third digit as A3, the fourth digit is A4, and so forth. That's okay. That's not so hard to do. It's just scanning and reinterpreting basically. And if you apply the Fourier transform, you're going to get some numbers in a row, right? Just like we did. I mean, if you did this trick, did the polynomial trick, you multiplied them together, and it will do the right thing, right? The second bit and the second bit will both be x to the 1, x to the 1, and it'll go to the x squared slot, which is this, yeah, what you want. So you're going to get carries. Well, each digit is 0 or 1. It's in binary. Coefficients. Okay, but you still have to deal with the n. Yeah, yeah, okay, so you'll get very large, it's n. So if you multiply the polynomials, you're going to get coefficients that are like, could be as big as n, right? That's what you're saying? And then something has to squish that down, and it's carrying all the way through. And I think this is why it was so hard to get n log n. It was dealing with carrying. But this is also why, at least based on reading just the first page or the abstract, they are trying to start with the Fourier transform and then fix some of these carrying issues. Well, be careful. So you can have like n over 2 coefficients, each of which are n over 2 big. So if you're doing it naively, where you're just kind of reassigning things, that's already n squared bits. Oh. Uh, well, first, if you get it down, if it's really simple, then you'll get at least an A in the class. But I think it's quite tricky to deal with the carrying correctly. I don't think it's quite so simple, and I think people have been very tempted to think it was going to be that simple. Maybe it is. Maybe we missed it, but you should try it out. But it's a very good question. Yeah. hmm so this pairwise multiplication where I'm getting the values of r. Now I'm just matching them up, right? Oh yeah, here I'm treating like multiplying two numbers as a constant. Yeah, sorry, we shifted gears a little bit. I'm not too worried about bit representations for this topic. Yeah. Oh, we haven't done that yet. Yeah, I'm just trying to get you excited. But this is just an application, multiplying polynomials. Okay, any other questions? Now we can actually do the, yeah? Oh, we're going to actually do the 2n Fourier transform, not the n. So we're going to evaluate at 2n values. Yeah, so if I take two n degree polynomials, r is going to have degree 2n. And at the end, I need to apply the conjugate transform to r. So that's why I wanted to always take the 2nth discrete transform instead of the nth to make sure that I have kind of enough data to recover R at the end. Yeah, yeah, but that's okay. You can still take a polynomial and evaluate it at more points than its degree. It is true that that's more than necessary to recover P. We do it because we want to recover R, which needs more data. Yeah. Okay. Any other questions? Okay, so let's try to show how to do the Fourier transform in n log n time. Then you can multiply polynomials. You can do other silly things on your homework very fast. Okay. All right. So the main idea we're going to leverage uh, is the fact that if I take the 2nth root of unity and I square it, I'll get the nth root of unity. Yeah, just something to keep in your mind, and I'll see if I can get you guys to guess. So, okay. All right, so let's say our input's like A, and it has two n values. Okay, and I'm going to somehow try to. Okay, so I'm doing an input of size 2n instead of n for some reason. It is what it is. The slides have been made. Okay, so all right, so this is what we want to do, right? I want to evaluate uh, this kind of thing. So in our output, if I just look at the kth output, that's the value at the kth root of unity. Okay, so that's why here uh, you have in particular this k in the top right corner. Okay, so I'm trying to interpret a as a polynomial and evaluate the kth power of the 2nth root of unity. Okay, all right. Yeah, so this kind of thing. Okay, so good. And so, okay, how I want to try to evaluate, yeah, maybe this is the fun part. So I wanted to do divide and conquer on something, or split the input up somehow. And the question is, how can we try to split up the input? Yeah. Okay, so in general, this whole term is a whole list of terms, right? And it's the kth one. And the kth one is taking A, interpreting as a polynomial P, and evaluating its value. And so I've just plugged it in there. Yeah, it's a little notation heavy. Okay. Sorry. Okay. So you want to make some sort of super ginormous polynomial stuffing everything together? Each tick around the circle? Hmm. Okay, so in general, we have a polynomial. I want to apply to every tick around the clock. This is just the kth tick in that equation. Okay, so yeah, so if I'm going to try to split, okay, so any other guesses? Yeah. Yeah, so this is a little bit like a natural guess might have been like, oh, let me take the first half of the coefficients and the second half and try to deal with them separately. But we're going to do something different, which I think is surprising if you haven't seen it before, is that we're going to split it up into the even and the odd coefficients. Okay, so the first line has the even ones, A0, A2, and so forth. And the next one has the odd ones, A1, A3, um, and so forth. I think this is a typo, right? This should be a 3. Yeah. Okay. So why is this so great? Well, okay, so now we have two polynomials, basically, right? In some sense, I could think of like the polynomial just consisting of the even ones, and the polynomial is consisting just of the odd ones. Okay. Somehow I want to take advantage of this. So, okay, like let's look at the evens, right? I want to find some very efficient way to kind of deal with this. I want to kind of reduce it to some kind of smaller fast Fourier transform, so to speak. Like right now, we're doing a 2n fast Fourier transform, the n 2nth one. It would be nice to turn it into the nth one. Yeah, perfect. So you can divide all the powers by 2 and then the da da da. So okay, so if you look at this, right, this is I've just ripped out the even part, okay, and because omega sub 2n squared, so that's 2 ticks, right? But if you square it, it becomes 1 tick of the smaller resolution. Okay, so this is just the algebraic identity up at the top. Okay, so omega sub 2n squared will give you omega sub n. Okay, so you can plug that in and you can reduce all the exponents by a factor of 2. Yeah, and so now what I'm looking at here is doing the nth fast Fourier transform on the even coefficients of the polynomial, whereas I used to be doing a 2n. Okay, so that's great. Yeah, so you can at least get that. Now we can do something similar for odd. It's going to be a little bit different, right? So for odd, mm, these are, I think this should again be 3. So sorry about that. Okay, so those are the odd coefficients. Okay, and how? Yeah. If you pull out one of these omega sub 2n terms, then you get even ones left. Oops. Then you get even ones left, and then you can do the same trick. Good. So get something like this. So if you can do the nth Fourier transform to the odd coefficients, then you can recover what you're looking for. Good. Good. Okay. So at some level, I've taken the 2nth Fourier transformed and turned it into 2nth Fourier transforms. Okay. And now how do I deal with these? We recurse. Okay, so we recurse. And that'll be the algorithm. Okay. Good. All right. So I guess this is some version of the code. If n is 0, there's nothing to do. If n is 1, you just evaluate it. Okay. And otherwise you do what we did. I'm going to take the even coefficients, the odd coefficients, and then combine it as you'd expect. Okay. It looks a little bit abstract, but this is just, if you kind of went carefully through what we did, that's the right way to combine it. Okay, so good. Uh, Questions about the algorithm? It's pretty magical. All right. Um, Now let's just model the running time. So if I let t of n be the running time of doing the nth Fourier transform, how would I model it? Yeah. Yeah, so you turn it into two problems with half as many coefficients and half as many values, plus big O of n. We've seen this before, right? Yeah. Huh? Yeah, I think just the last line. Plus, like, yeah, to split it up into A even, A odd. Yeah. Otherwise, it'd be really fast. Um, yeah. Okay. Um, and what is this? Yeah, we've seen this before, right? This is just like merge sort and log n. Okay. All right, any questions? Okay, we have some excitement outside, uh, and we have about 10 minutes left, which I meant to load up with problems, but I got distracted. So here are then some problems that'll maybe help be good warm up for the homework. Okay, so here's one. All right, so let's say that I'm multiplying two polynomials. We'll do this one first. A1x, okay. One of them has n coefficients, and what I want to do is, what happens if the polynomials have different size? Say this one only has k terms, and k is something much smaller, okay? So given this, I can certainly imagine q was just a bigger polynomial and multiply it n log n time, okay? But my question is, can you figure out how to do something that's more like n log k time? Okay, split what? Okay, all right, that was quick. Don't worry, there's more questions, but let me go over the idea. But at least this is a good, clever kind of thinking, right? So uh, sometimes a student is tempted to reinvent the wheel, go back into the proof, and somehow try to customize it for this uneven case, right? But the suggestion was in many ways lazier, but also more elegant. What we can also do is split this polynomial up into groups of n over k, sorry, groups of k coefficients each, right? So the first group might just look like a0 plus a1x plus dot 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 plus a to the k minus 1, x to the k minus 1. That will be one group. It's a degree k polynomial. And then the next group is going to be the next k terms, but you can shift out an x to the k term. So you have x to the k times ak plus ak plus 1 times x all the way up to a to the 2k minus 1, x to the k minus 1, right? So normally it would be x to the 2k minus 1, but I've pulled out an x to the k. So you can keep doing this and just partition your input the bigger polynomial. Yeah? Oh, okay. Well, then I'll finish this and then we'll get to it. And now what you're left with is, oh, okay, what I can do is I can take each of these and multiply it with this one, okay? And then I'll just add everything together at the end. The adding won't be very hard. So at the end, you end up doing n over k, times multiplying polynomials to degree k, that's k log k, and you get your n log k. Okay, so uh, yeah, but it's a good style of thinking to wonder if there's a clever way to reuse what you already have. Okay, other way of doing it. Okay, so I never considered this. So let me go through it slowly. Can you do some kind of division? All right, so use some kind of division algorithm with some kind of remainder, I guess, right? So you're going to write p of x, and if you once you do the division, first of all, does the division take a long time? Uh, you get a of x, q of x plus b of x, right? Where b of x is it's kind of like smaller than q of x, like in a certain ring space. Is division also FFT? Actually, what's the best way to divide polynomial? Can you do it with FFT? I never thought about this. Uh, yeah, I'm a little bit worried about how fast you can do this. But let's say for some reason you can do this magically. What would come next? Oh, okay. So somehow AXQX squared plus BX or something? QX? Okay, so at some level, it's still an interesting idea. So B will have smaller, it will be degree at most the same degree as Q if you kind of went through this carefully. So this will be a nice small K log K multiplication. And then here you have Q with itself, so that'll also give you some K log K. And then somehow A should be much smaller, right? Because you should have gotten rid of like K degrees. So A should have like shrunk by a factor of K, should be like degree N over K. And now we just have to deal with these two. And you have two, and then you can try to recurse. Good point. You're going to get n minus 2k and you're going to get k, the 2k. And then next time you'll get like probably n minus 6k and 4k or something. Oh, okay. We can start trying to do this doubling trick. Uh, so one thing I would just be a little bit worried about though is that each time we double, so normally we do the doubling trick, the dimensions of that object at play don't change. So if I'm multiplying n by n matrices together, I get another n by n matrix. So like getting a to the fourth from a squared is the same effort as getting a squared from a, same effort as getting a to the 16 from a to the 8. But here your cubes are getting bigger and bigger, and we have an algorithm that's sensitive to the degree. So it's not obvious to me that this will, it's still fun to do creative things, but I'm a little bit concerned about this. Yeah. Yeah, if division is slow, then we're screwed anyway. Well, we used to think multiplication took nk as well, and we got it down, so. Yeah, I don't really know what I mean, we think that this running time probably wouldn't be very good in any case. But if division takes n times k time, like the old-fashioned way, then you're already lost. 'Cause we're trying to get n log k. If you could do it faster, I kind of forget. Yeah, let's see. Oh, now we're down to 2 minutes. I guess there's no time for more problems. I'll tell you one that's in the book, and maybe it's fun to think about. Um, if you start looking at polynomials of the form with two variables, uh, pxy, qxy, right? So now you start getting like weird things like a00 plus a10x plus a01y plus a11xy, right? A multinomial, okay? And let's say that this had like degree k and this had degree L, okay? So a naive thing would be something like nk times nk. This is sort of like, it would be like for loops or something, right? Sorry, kl. It would be kl times kl if you did it the old-fashioned way with loops, okay? And I think if you're clever, you can try to think about how to get something more like KL times log of KL, which is sort of like, extends what we did together as a class. Yeah, so this is fun. I mean, obviously this would be practical too. Once you can do this, you can start doing more interesting things. Um, but there may be some clever ways to do this as well, where you don't necessarily have to reinvent the wheel. Sorry? Y is equal to x to the k? Oh, that's how you're thinking about it? Yeah, yeah. Okay, I think you have some reasonable ideas. But yeah, try to think of cute ways to try to reduce multinomial down to single nomial, and this will fall out. Can you use the Fourier transform if n is fractional? Um, can you use the Fourier transform if n is fractional? My instinct was no, but then I'm always afraid that, oh, there's some way to do it. But certainly what we did today was much more natural for integer n. Yeah, and probably actually what you want to do to make the divide and conquer nice and easy is whatever integer you get, round it up to a power of 2, that at most doubles n, and then you can always keep dividing in half cleanly. So just embed it into the next power of 2. Yeah. Okay, anything else? We're about out of time, so. Okay, so that's going to be it for divide and conquer for us. And then Tuesday we'll start something called dynamic programming. Thursday I want to know